Hello and welcome to the demo. This demo is going to be a little different than what we traditionally do. So this demo is going to kind of bridge between the didactic material or the lecture and also the actual physical homework. When learning about neural networks, it's both easy and hard. And I said that in the announcement. It's even hard to kind of explain it. So neural networks can be super simple. Okay, and a lot of the reason they can be super simple is because now we have these great libraries that we can literally just type a few lines of code and boom, have a neural network. That is your homework. Your homework is basically type or copy and paste a few lines of code and give me a basic neural network. Okay, now does that mean you really understand the neural network? No, of course it doesn't, and I know this. But on the opposite end of the spectrum, you can learn all the math and do all the not using any libraries and literally code a neural network from the ground up. And then you're not using your time efficiently. And that's not really the scope of, in my mind, business intelligence. Okay? Business intelligence is to take data and get to a result. At the end of the day, that's all it is really about. And other people might disagree and argue, but really, you have a chunk of data. You have a lot of data. You have a question, and you got to get to an answer. So, and I don't want to say the fastest method is necessarily the best method, but a method that produces a level of accuracy and that is repeatable and that you can scale, those are the preferred methods in business intelligence. Well, coding everything out by hand is not going to get you that way. Doing everything all automatic is not going to get you that way either. So you have to be in this kind of middle ground between having some type of deep understanding and having just a tertiary, a basic understanding of neural networks. So, as I alluded to in the announcement, I have 3 demos of neural networks. One's super high level, and like I said, I've added as many comments, I've added as many pictures. I've updated to run on the newest version of Keras. I've done everything I can to really give you something that you can look at and be like, oh my God, I can understand this. This is English. And that's my goal. Then I have one notebook where I'm going to go over a Max Min and a couple other, somebody, a guy named Elvis wrote it out and I kind of updated it a little bit. But it goes into much more detail. Everything is defined as a function, just so we can kind of visualize in our head what's happening under the hood. And third one, I think what the third one is. I don't remember what the third one is. I actually have it up here behind us. But we'll go over all 3 of those in this video. Now, just as my personal experience and my personal journey to learn machine learning, it's always gone one of 2 ways. And that's why I'm trying to bridge the gap. One method of learning machine learning is, maybe take a class or a CS-based machine learning, and they say, hey, here's what machine learning is. Let's go into the math. And then you spend, and I'm not joking, 2 weeks going over how the math of MSE or the perceptron or something works. And so now you have this really good understanding of how math, how everything gets updated. And you go to code and you're like, well, I coded a super simple, non-scalable, non-production ready 3 lines of code that's all math based, and it doesn't really help anything. Or the opposite end, which is kind of your homework, to be honest with you, is you get these tests on this iris data set, which is this leaf petal, and you're like, oh, hey, look, I did machine learning, and I can predict the length of the petal or whatever. And then you go to do your own project, you're like, oh my God, what I learned was completely useless. So that's why I'm trying to do this kind of hybrid thing, where I teach you some of, I'm going to let this play. This is just a demo of a neural network, and when I first saw this, I loved it. So if you can watch this and listen, that'd be amazing. I'm not going to watch the whole thing. But that's why I'm going to try to do this hybrid, where I go over something simple, I show you something more advanced, then we go something kind of in the middle ground, and then your homework is to come up with any neural network. Now for the homework, we'll talk about, you can Google, there'll be another video about it. It's not going to be hard. Don't make it something that it's not. But the thing is, though, you can start playing around with your data. You can submit the homework, the MVP, submit the homework. Super simple, maybe 8 to 10 lines of code. Submit the homework, then play around over the next week. Or Google other demos. You can submit those. I'll be very liberal with the grading, as I always am. the goal is to submit a neural network, a learning neural network. So as long as you do any type, it can be recurrent neural network, it can be CNN, it can be, anything. I'll be pretty happy as long as it's a traditional neural network. I love this demo. Every time I see this, I just love this demo. Also, I realized too, in one of the videos, I don't know if it was an RNN or CNN, I talk about back propagation. And I didn't make it super clear. Most or all, I can't use that word either, most neural networks do back propagate. Okay? However, a recurrent neural network has a recurrence loop, a loop where it can adjust the weights in through time. Okay? So where traditional ANN, it does back propagate after it runs through the data. A recurrent neural network can basically update the weights before it runs through the data. Okay, so I just kind of wanted to make that clear. I don't know what video I said it in, but I thought about it. I was driving. I'm like, oh my god, I didn't really explain that clear enough. And if you have questions about that, let me know, and I can try to help. I guess let's move over to the actual homework. Yeah, it's like I said, neural networks are kind of hard to visualize and to understand, but once you get it, then you can't forget it. So. Okay. And so like here, this is literally the homework. You do something like this, boom, it's easy. I mean, it's 3, 4, 5, 6, 7, 8, 9, like 15 lines. Okay. And I give demos, and there's a bunch of them. There's a bunch of different ones you can do. So let's start at the very beginning. Okay, this is, again, another one of the problems with machine learning is a lot of the demos out there are older. Okay, so you hit a demo, and boom, it's 3 years old, and none of it works. So I've verified all these demos work. I've changed them. I've optimized them. I made it as simple as possible. I've added graphs. So this looks at to classify breast cancer tumor as benign or malignant. Okay, it's a super simple data set. Let's switch to this OBS. 1 second here. Screen. Here's a data set. Okay. And don't ask me what half these mean. I'm not a pathologist. Mean area, compact mean area. And there's a data dictionary on here. Okay, so this is just what the data looks like. Let me switch over. No. And okay. This kind of gives you an overview of what's going to happen through here. We select variables, we decide the number of nodes, present data, propagate features through, adjust the weights, calculate the actual output, and error in output. So right now we have 357 benign, 212 malignant, samples. Most of these things, like I said, we're using Keras for this one. I put this up on Dropbox for y'all, so it automatically loads the data. After the class, the link will probably die. So if you want, you can just download it or just Google, I don't know, breast cancer ANN, or I can email it to you. But you can save it if you want. So Pandas, NumPy, Seaborn, Scikit, just to do the test train split, and to do scale or max-min, which we'll cover in the next one. So I've tried to label, here, let's just load this. Pause it, so we don't really need to watch it load. Okay, so you're getting your requirements here. You're loading it directly from the web. Here's just a head of basically the data, so we can kind of see what it looks like. So now we're basically going to split it into X and Y, what we're going to basically train on. Okay, so I guess, so basically, let me move that. So what this is doing right here is X is basically the features, and so then Y would be the answers. And that's, I guess, kind of one way to think of it. Y is also called sometimes the labels. When you see that colon like that, that just says, hey, take everything, take all rows. So we're taking all rows and all columns. That's basically what that colon is. So the 2 is basically we're taking everything from the second column, third column, and going forward. Yeah, I guess that makes sense. So now the problem is that if we have categorical data, so categorical, what is categorical? First place, second place, red, blue, green. Well, guess what we have? Malignant and benign. Okay, so we can't use. So I'm talking about here, right here. I wonder if I can zoom in. Control plus. Look at that. So right here. So we can't use that in terms of, hey, malignant or benign. So why don't we just convert it to 0 and 1? Make life easy. Okay, so that's kind of what that code does right there. Let's see, what are we at here? Random state. Oh, you know what? I did change this because I was playing around with it. Or you can even go 0.1. Sorry about that. So basically this says, hey, the test size, the data that will be used for testing is 10%. Okay, random state, you can use this for reproducibility. I added this just recently because I wanted to make sure you guys could like reproduce the same answer. One of the problems with machine learning is sometimes you don't always get the same answer, so I added and also downloaded some more random state stuff. What else? Okay, so this basically takes our features and scales them to from like 0, 1, or I think that's what that one does. Basically, why do we want it? Because, so, you know, the great example of this one is the house example, the Boston house example, or any of the house data. So you might have the number of bedrooms from 0 to 5. Then you have the price from, I don't know, $1 to $10 million. Well, the scale of those features is so different, it's sometimes hard for the machine to understand that. I guess that's really the best way I can explain it easily. So what we do is we basically just look at the max and we say, hey, here's a max, and we divide everything by that, and we basically scale it to basically like a standard deviation. Okay, there's on the other one in this second notebook, I'll go into that a little bit more. This basically just creates like an empty neural network. It like creates, this gives an empty neural network that we can basically add layers to. So here's our layers. And we're saying, hey, we're going to take 30 dimensions, 30 columns, 30 features. And we're going to get it down to like a 16 unit model, 16 nodes. That's kind of our first input. Now, I tried getting different dropout rates because it just learns so fast. It's hard to see it. But basically this says, hey, this is how we're going to kind of do a dropout rate. It's how we update our models. Really. So we'll do, did I put something in here? Dropout rate, I did not. Maybe I should put a little description. Basically the dropout rate kind of prevents overfitting. That's easy enough. So now the second layer. Okay, so you have your inputs, and then you have, you know, the things. That's your first layer. This is your second layer. So we're talking the second layer. Is your, to pick a picture on this one. There's a picture on the other one. Okay, second layer. That is here. Okay. Same dropout rate, same basic thing. Like I said, I tried to make it as easy to understand as possible. Put a lot of text in there. Right here, like my second layer. Now, at the end, we want a sigmoid classifier, and there's a bunch of different classifiers you can use. But I just put a picture of a sigmoid from 0 to 1 to show, I guess, what the sigmoid is. This actually came with the notebook. So, you know, classifier, you know, hey, just basically give us a sigmoid function. Okay, so now start with Atom, or okay, so optimizer equals Atom. That adjusts how the model learns, basically. And I guess I could just Google real quick what Atom's just what, you know, a lot of people, there's a couple other ones, Atom Optimizer. Yeah, there's a couple other optimizers. I just Googled this really quick, but here's a different an article about different optimizers. Whew, it's hard to speak today. Stochastic gradient descent, you know, is just a way to optimize, to find, I guess, the best training method for your neural network, um, the best way to correct weights. Easy way to kind of explain it. So we're not really going to go into that. Let's see, but that's basically what this is. Loss as binary cross entropy. So this function will, that kind of measures how well you're doing, I guess. Yeah, it does. And then you see metrics equal accuracy. You can go to Keras and get there's all different types of ones, different accuracy measurements, MSE, and a bunch of them. So there's that. Let's see what else we have. I deleted this. I guess I should move that up to the top. And here's where we actually do the training. Where did I leave off here? Actually, went off. So that explains that. So let's just recap. Libraries kind of split the data. Once we load the data, then basically take benign and malignant and kind of assign it x to 0 or 0, 1. Sorry. Split the data. Scale the data. Normalize it so it's in some type of scale. Create a neural network. And create your first layer. Create your second layer. Create your output layer. Okay, how we're going to kind of train or use a layer. Yeah, it's a performance classification. Yeah, there we go. See, just set some random seeds, and did a lot of updating to this code. But basically, you don't need history. But the only reason I'm using history in here is just so I can plot and show you the graph of training versus validation. And you see, it starts. It generally starts off at 60. Let's see where it starts off at. Yeah, 60. And you see it almost goes up to 100% accuracy in 10 epochs. Okay, so, I mean, it does really well. So, I mean, generally, you could train this thing on probably 10 or 15 epochs, save a bunch of time, and you'd be good to go. But I just kind of want to show you this. So, there's that. So, this is basically the model accuracy. How accuracy is it? Now, what's another way that we show that? We do that by a confusion matrix. Okay, so this is negative that were identified as negative. This was positive that were identified as positive. These are your false negatives and false positives. We see we only have one. That's pretty good, you know. We have a 98.2% accuracy. Actually, times by 100. So, I mean, and if you get rid of a lot of the comments, this is only a few lines of code. And it's training, I mean, we're not using any GPUs. This is just literally just training on the CPU. I mean, here, we can cut this down to 15 or 10. Restart and run all. And you see that it trains relatively fast and it does a great job. It takes longer to load the libraries than it does anything else. Like I said, I want to include as much text as I could so you really can kind of understand the code. Yeah, see, I mean, look at it, still 100% accuracy. There we go. So I'll give you a copy of this code. Feel free to use it, feel free to change it, feel free to play with it. You know, once you download it, just save it, make a copy, and play with it, you know. So there's that one. So the next one, this is the one by Elvis Savary. I did a little bit of updating to this, but this is a PyTorch build. I guess I'll run it all. This one I'm not so worried about you running. I want you to focus more on just the high level of what they're doing here, okay? So sorry, I'm pretty comfortable in my chair. one of the things I really like about this is how simple the data set is. So his idea was that he represented the amount of hours studied, how much time sleeping, and grades. Okay, so you can really easily visualize it. I mean, there's what, three observations. So X, let's just read this really quick. X represents the amount of hours studied and how much time the student spent sleeping. So this student spent 2 hours studying, 9 hours sleeping, got a 92% on the test. This student spent 1 hour studying, 5 hours sleeping. I might have that backwards, but it doesn't really matter. And got 100. This student did 3 and 6. Okay, so I mean, you can really visually see the data. Now, instead of using the scikit-learn max-min, he just coded it out by hand. Okay, this is useless. So what we'll do is, where is code? So let's just print x move print x. Let's do it. Okay, so if I was to take 3, okay, so let's think about this for a second. So what I want to do is I want to look at the max number, the largest number. 2, 1, and 3, what's the largest number? 2, 1, and 3 is the largest number. So what we're going to do is we're going to take to scale everything. And you can find articles on scale, but this is, I mean, I like the way he breaks it out here. It's just super easy. So if we take 2 divided by 3, we get 0.666. Okay. We take 1 divided by 3, we get 0.333. We take 3 divided by 3, we get 1. Okay. 9 in this second series is the highest. We take 9 divided by 9, we get 1. I'm not sure exactly what 5 divided by 9 is, but I bet it's 0.55556. So we scale those features so they're all the same. So the reason we do this is so that we have like a common ground, a common basis to observe from. Okay, this is often called max-min or scalar. That is what this code does right here. Okay, but just instead of calling a function, instead of just calling a feature, it's here's actually the math behind it. Find the max and do a division. Okay, I mean, so that's what I like about this one, but it goes into a lot more detail. Now, you don't normally need to know that detail, but if you don't understand, if somebody asks you, hey, what's max-min or what's a scalar feature? Well, I don't know. Well, that's not an acceptable answer. But if you say, hey, a scalar feature basically takes the whole range of values and compresses it from either like -1 to +1, from 0 to 1, or to the max to the minimum, and just kind of compresses it down. It uses standard deviation. There's different ways to do it. But basically, it just takes all the different data sets, and some of them have really high values, and some of the columns have really high values. Some of the columns have really low values. And you kind of scales them on the same scale. That way we can have a fair comparison. Okay? And I mean, we can think about this in college. What do we do in college? Well, some classes have 10,000 points available. Some classes have 10 points available. But you know what? At the end of the day, you get A, B, or C, or I guess D or F, in all your classes. We scale all the classes to A, B, C, or D, or F. I guess there's no E, A, B, C, D, or F. So that's a scale that is universally accepted. So, if my class, I think there's like 500 points, and maybe another class, there's only 100 points available, how do you compare the two? Well, you compare the two by, hey, you scale it to an A. You scale it to a B. And we go in here, and 1 second here. Let me fix this real quick, and I'm sorry I had to go get more copy, but I was just thinking about that. I should make like an intro to machine learning class, make like 10,000 points or something ridiculous, make every assignment worth like 100 points, and then see if anybody ever lists on the resume, I got 10,000 points on Intro to Machine Learning class at UNLV. That would be funny. So here, you kind of see, again, so in Python, these are just your definitions. defining a function. Okay, so this is, okay, input 2, hidden 3, output 1. Again, because why? The output is, let's go back up here. It will try to take a guess from what it has learned. Remember, the neural network single input which we use to predict the grade using the parameter. Okay, so that's kind of what we want to know right there. So what else? The sigmoid function, which we showed in the last video. That's a little graph from 0 down. Sorry, from 0 to 1. Here's a sigmoid function. Here's just a function of it. Back propagation. Training. So you see how everything is broken out here. So let me run it all. Now, this thing runs instantaneously fast. Why do I include this? Because it does help to kind of, did I hit wrong? I did. Does help to kind of see it manually broke out. Okay. Now, I don't expect you to ever do this. I mean, maybe you want to go back to college, get a PhD in machine learning and CS, then this would be what you could do. But, I mean, right now, Keras, PyTorch, a million different programs can do this 10 times easier. But the thing is, though, at least now, you can kind of see what's under the hood. Does it help? I maybe it does. Maybe it gives you a little deeper understanding of some of the things that goes on. If I ask you what is the formula for speed, was that distance over, what is it? I can't think now. Speed is distance over time. Yeah, there we go. What a total brain fart. So if you're doing 55 miles per hour, the vector for that is the distance. You travel 55 miles over 1 hour. Okay, that's 55 miles an hour. So now we know the formula for speed. How does that help you deal with drunk drivers? How does that help you deal with shitty drivers? It doesn't. Maybe if somebody asks you, hey, I know that when I'm going 60 miles per hour and it says, hey, the exit's 2 miles away, I know in my head that's about 2 minutes away. That helps, kinda. But at the end of the day, knowing the formula for speed doesn't really help you. Knowing the different types of engines may or may not help you with a car. If you have a fuel injected car and you know how to rebuild a fuel injector and rebuild an engine, but you get a flat tire, maybe those skills aren't transferable. So, just glimpse over this notebook. That's all I ask. I mean, you can run it. I'll give you the code, everything else like that. Maybe the max min helps a little bit. Maybe actually seeing the network input size 2. Your hidden size 3. Seeing how hey, here, like I said, in Keras or even in PyTorch, there's easier ways to define sigmoid functions, your outputs and stuff like that. I don't know why he puts it inside like rather weird, at least to me. Cut. Cut doesn't work on my keyboard. Oh, you know what? That's not. That's why. So, pretty, kind of pretty simple explanation, but like I said, I think you can kind of understand it. And again, this is just a high-level overview of what's underneath the engine. So our final notebook is this one. Again, I mean, I looked at notebooks that were relatively well documented and that had a decent amount of explanation. So don't get too caught up on all the documentation, on all this. The code cell is not a huge amount of code cell. Again, I put it up on Dropbox just to make life easier. Yes, let's go over it before we run it. import the library. It just uses TensorFlow. You see, it's super simple. We use TensorFlow. We import the data. Okay. Our answers and features. You print it if you really want to. I don't know if that really helps you. Okay, label encoder. So the label encoder is, again, hey, sorry, I gotta get my chair adjusted here. We can't really encode things like Spain and France. We have to, we have to do either one hot encoding, or this one they're doing gender, but we have to say X for female and Y for male or whatever. As long as you remember, it's fine. So that's all this encoding data does. That's all the label encoder does. One hot encoding for geography column, which I thought we were doing up here, but we're not. We're doing gender, and we're doing geography. Okay, so we're getting rid of words and moving them to numbers. Splitting the data set to test and training. Okay, boom. So if you can see this here. What are we doing? We're testing 20% of the data. We're going to train on 80%, test on 20%. Scikit-learn. So easy enough. Hey, look, we're using the same scalar. So instead of doing that, hey, find the max, divide it. No, we just use this. Okay. We're creating a neural network. We're creating the framework to hold our data, or to hold our neural network. Adding input layer in the first hidden layer. Boom. Adding a second layer. Adding the output layer. I mean, I specifically look for things that are very, very clean, very easy to understand. Then what do? We train it. Okay? So what else? Predicting results. The confusion matrix. I guess I could have made this one a little better. I haven't really edited this set. I'm not a big fan of you can kind of see it that way. You can, if you wanted to, if you really were interested one day, you'd throw this to history equals and train it that way, and then grab your confusion matrix and make your confusion matrix prettier. That's all this is, basically the same thing. And this is just code. Because again, the person that originally coded this just had that type of confusion matrix, I believe, so I just made a little better confusion matrix so I can visualize it. You do the same thing here, but it's the same basic concept. 85% accuracy. There we go. Okay, and we're not going to worry about any of that stuff down there. So let's just run all. Super simple imports. Using TensorFlow 2.14. Pull some Dropbox and you see the data right here. See gender, female. So we need to fix that. That's what this down here does. And then country is somewhere over here that we use. The scalar, build the ANN. Training. So you see how we're starting to get better at training. Let's go down here just a little bit. 86. Again, this is just a straight non-GPU machine. This is just using a normal CPU. I don't have a GPU attached. $100 might still be overkill for this, but still. We're just hanging there. When in doubt, reboot and rerun. Yeah, the reboot and rerun just worked perfectly. 85% accuracy. So again, not super complex code. It's very clean. A little bit more complex than the first one, but not by that much. We do 2 encoders. A little bit better description. So And that pretty much ends this part of the demo. If you have questions, let me know. I'll do another video just on how to complete the homework. So this hopefully gets you a better understanding of the actual code that underlines and runs neural networks. Okay. You don't have to make this something that's really not that complicated, but once you start getting into questions like, hey, what happens if I change the activation feature? Or what are different activation features? What are different optimizers? You start looking into these things, start playing around. Well, the problem is when you deal with data that's like, I don't know, the Iris data set, you just don't have that comprehension. You don't understand it, and sometimes they're not always the best well written. So we really did try to spend a lot of time on these 3 notebooks, well, on 2 of the notebooks. Somebody else wrote a lot of this too, but trying to document the code for you so you can kind of understand it. I mean, look at this. I mean, how easy this is. A very small data set, which makes it really nice and easy to understand. Same thing with this one. So if you have questions, let me know. I'll help you in any way I can. We can schedule one-on-one meetings to go over any of these things. I think, like I said, very easy. This one's considerably more detailed. But again, well documented and at least enough detail that you can kind of understand it. And this one is like the hybrid between the two, at least in my mind. So if you have questions, please let me know. Do the homework. Watch the homework demo, which is going to be very similar to this. Thank you.